Section: Introduction. In this section, we discuss the significant resources needed to train large language models, LLMs, and the pressing need for efficient tools that can assess proposed changes to their architecture or training data without requiring extensive training. While much research has focused on small models or theoretical approaches, one of the key tools for practitioners is the estimation of scaling laws for LLMs. A scaling law allows us to predict the performance of a larger model based on the performance of smaller models that share the same architecture but differ in size and training data. Typically, to create a reliable scaling law, we need to train models within the same family, varying only in their parameter count and dataset size. Most previous studies have trained a wide range of models exhaustively to establish these laws. However, we recognize that practitioners with limited computational resources may struggle to determine which smaller models to train to best estimate the performance of a larger target model. Our paper aims to provide practical guidance on how to effectively use small models to make reliable predictions about larger models, balancing the number of models trained, the size of the largest model, and the dataset size. We start by gathering diverse model data for a comprehensive meta-analysis of scaling laws, moving beyond the typical narrow focus of previous research. We explore several important questions regarding scaling law estimation, such as the reliability of extrapolating scaling laws, the variability of scaling law shapes across different model families, and whether scaling laws must be derived from fully trained models. We find that while larger models generally yield better estimates, training more smaller models can also reduce variance and improve reliability. We define a scaling law as a method to estimate the loss of a costly model by training less expensive ones that share a pre-training process but differ in hyperparameters like model size and training tokens. This allows us to make informed decisions about which large-scale model to pursue and optimize hyperparameters within computational limits. Throughout our analysis, we will not differentiate between partially trained models and those trained to completion on a subset of the largest training set. We will use a common functional form for our scaling laws, which captures the general performance of the model family and describes the scaling effects based on size and training tokens. Our goal is to provide empirical insights into these scaling laws, starting with the necessary data collection. Section Summary. In this section, we discuss the challenges and methodologies for efficiently estimating the performance of large language models, LLMs, using smaller models, emphasizing the importance of scaling laws that predict a target model's performance based on a family of models with varying parameters. We outline our approach to gathering diverse model data for a meta-analysis of scaling laws, addressing key questions about their reliability, the impact of model size, and the optimal training strategies to minimize costs while maximizing predictive accuracy. Section: Data for 1,000+ scaling laws and more. In this section, we present data on over 1,000 scaling laws. We have gathered and made available the largest public dataset that details scaling behavior across various model families. This dataset compiles information from numerous training efforts of large language models, LLMs, that have shared insights about models of different sizes. While our experiments focus on scaling laws related to loss, the dataset also includes performance data on downstream evaluation benchmarks when available. We specifically looked at language models with more than 3 billion parameters, using data that was shared publicly or through private communication. We welcome further contributions and requests for additional data. Additionally, we manually extracted information from papers that reported losses in figures but did not release models. For each model in our dataset, we provide details on any downstream evaluations and losses measured during training, along with calculated metrics, links to relevant checkpoints, data sources, and information about computational costs and training epochs. Each model is uniquely identified by its name, type, architecture, and seed. Our dataset includes models like Pythia, which has the largest variety, as well as Opt, Olmo, Amber, K2, Mamba, Red Pajamas, Module Former, and various transformer architectures like Bloom and T5 Pile, among others. The dataset encompasses 1.9 million training steps evaluated on loss or perplexity across 485 unique pre-trained models and over 40 scaled families. We believe this resource will be valuable for the community and plan to expand it as new models and training dynamics are shared. Regarding scaling law estimation, we identify the maximum parameter family for each model family and estimate a scaling law using the remaining models. We use a fitting function from scikit-learn for this estimation, although we found an alternative solver to be less stable. We only estimate scaling laws for families with at least 3 models. To evaluate the accuracy of our estimated scaling laws, we account for loss fluctuations during large-scale training. We test against several checkpoints near the end of training, selecting target models based on the maximal token family defined earlier. We report the mean absolute relative error between the empirical loss and the predicted loss from the scaling law. To determine the usefulness of a scaling law for practitioners, we examined past experiments where A/B tests were conducted. We found that meaningful changes in model accuracy were typically associated with at least a 4% relative difference between models. Additionally, variance across random restarts of the same model architecture can reach up to 3.5%. This suggests that a scaling law should aim for a goodness of fit that meets or exceeds these thresholds. For example, Pythia 6.9b models showed a 40% difference in loss due to code inconsistencies, while a data deduplication A/B test resulted in a minor 5% loss change. We also observed that training models with different amounts of data or epochs led to varying effects on loss, with some changes reaching up to 10% or more. Section Summary. In this section, we present the largest public dataset on scaling behavior across various language model families, aggregating data from over 485 unique pre-trained models and 40 scaled families, focusing on loss and downstream evaluation metrics. We also describe our methodology for estimating scaling laws, emphasizing the importance of accuracy in predictions and the minimal effect sizes that are meaningful for practitioners. Section: When I train a new model, do I even need a new scaling law? In this section, we explore whether we need new scaling laws when training a new model. Scaling laws connect model performance to training parameters like model size or dataset size. When we make discrete choices, such as selecting a nonlinearity or a data preprocessing method, it's not clear how to combine information from different models with these varying traits. We notice that even pre-trained models with the same parameters can show different loss values, indicating that these differences matter. To understand how choices in architecture, training methods, or datasets influence scaling laws, we can examine how the estimates for scaling law parameters differ across model families. Our findings reveal significant variations in these parameters among different families, suggesting that the way additional data or parameters enhance performance is influenced by the model's architecture. This implies that understanding a new model family might require developing a new scaling law. We also investigate how accurately we can predict a model's final accuracy by borrowing parameters from scaling laws of other families. Even if this leads to less precise estimates, it might still reflect large-scale model behavior. We fix certain scaling parameters based on previous studies and estimate the remaining ones for each model family. Our results show that sometimes, just one training run in a new model family can yield accurate scaling law predictions. For instance, in the Olmo family, we achieve less than 1% error when estimating the accuracy of a 7 billion parameter model using data from 1 billion parameter models. We find that a constant scaling factor works for most models, except for the encoder-decoder T5 pile. However, we observe that error rates are higher than in the source family, especially for larger models. Next, we consider whether we can predict losses using partially trained versions of the target model instead of smaller models. When estimating within the same family, we find that the scaling term remains constant, and we only need to extrapolate for the other parameter. This method proves useful, given computational limits, and suggests a promising direction for future research to enhance efficiency in scaling law predictions. We also establish two baselines for comparison with our predicted scaling laws. These baselines assume that the target model performs no better than the best model from the smaller family used for estimation. We find that the best performance baseline is closer to our predictions, as expected, since the target model generally outperforms others. However, both baselines show significant error rates, often exceeding 10%. Finally, we address how to utilize our data effectively. Previous research typically trained separate models for each parameter value, assuming that changes in the learning rate schedule made intermediate checkpoint losses unhelpful. However, recent studies suggest that learning schedules can be effective without knowing the full dataset size, prompting us to reconsider the assumption that only one useful data point comes from each training run. We test whether including intermediate checkpoints from all models in a family reduces error rates. Our results indicate that using full training curves for scaling law estimation leads to better predictions, as relying solely on final performance yields poorer results. Thus, we incorporate all intermediate checkpoints in our scaling law fitting. Section Summary. In this section, we explore the necessity of new scaling laws when training models, highlighting that architectural choices significantly impact performance scaling, and we find that using intermediate checkpoints from training can enhance accuracy predictions for scaling laws. Our results suggest that even a single training run can yield reliable predictions, and incorporating full training curves is more effective than relying solely on final performance metrics. Section. Should I use all intermediate checkpoints? In this section, we explore whether we should use all intermediate checkpoints during training. We present a plot showing the average relative error, R, for various token families when we only consider the end of training. There isn't a clear trend indicating if we should use all data or just a portion, but we find that the best estimates usually do not come from the end of training alone. We notice an uninformative phase at the start of training, which often shows spikes or increases in loss, suggesting worse performance. Therefore, we propose that this initial phase should be excluded from our scaling law analysis. Our experiments compare errors with and without including models trained on fewer than 10 billion tokens. We find that the very beginning of training can be detrimental to predictions and tends to introduce noise. For some models, like OPT and Pythia, the error is over 15% when using all data, but drops to between 4% and 10% when we ignore those initial tokens. We also discovered that cutting fewer tokens leads to noisier results, while cutting more has little effect. Next, we examine how to determine the size of the model we should train. We compare scaling laws while controlling for the amount, percentage, or size of the models. We find that selecting models closer in size to the target model is generally effective, but the impact is not strong or consistent. For instance, using all data often results in one of the lowest errors. In some cases, like GPT, Gopher, and OPT, even the smallest four models can achieve less than 10% error. However, in Pythia, the smallest models do not perform well, while larger models provide a similar fit. While larger models are beneficial, predicting across many scales can still be reliable, especially when considering other factors. We note that training additional larger models before fitting a scaling law can sometimes reduce accuracy due to increased variance in performance. Identifying whether a seed is particularly high or low performing is challenging without extra information, and cross-validation does not help in this regard. To address this instability, we suggest diversifying our training by using different hyperparameters rather than training multiple seeds. Finally, we discuss how many models are needed for reliable predictions. We observe that using larger models generally leads to better results, but due to computational constraints, we may prefer smaller models. Our findings indicate that having more models can reduce the error, even if they are not larger. Adding a larger model helps improve predictions by increasing proximity to the target model and the number of models considered. However, we also see that a single model can negatively impact overall predictions. In general, increasing the number of models tends to enhance prediction accuracy, as seen in our results with GPT-3. Section Summary. In this section, We analyze the impact of using all training data versus only the latter portions, finding that early training data often introduces noise and should be excluded for better predictions. We also conclude that while larger models generally improve accuracy, increasing the number of models, regardless of size, tends to enhance prediction reliability, although the relationship is not always straightforward. Section: What parameters do I actually need to estimate? In this section, we explore the parameters we need to estimate. We focus on whether some of the errors we observe arise from model misspecification, particularly regarding the functional form of our model, which has largely remained unchallenged since its introduction. We specifically assess if scaling laws show fewer degrees of freedom than previously suggested. To do this, we calculate the main components of the 5 learned parameters and discover that 3 components account for nearly all the variance among them. Our analysis shows that 2 of these components are closely linked to pairs of parameters related to the same training aspect. When we plot certain parameter values against each other, we observe a clear linear relationship, even though there are nonlinear interactions in our equations. However, we note some exceptions. The encoder-decoder model T5-pile behaves differently from other scaled families, and 4 additional families show a distinct relationship between 2 specific parameters. These outliers share a common trait of being trained with multiple passes over a single dataset. We suggest that future research could explore different functional forms that connect some parameters or introduce new ones. Additionally, we recommend considering the learning rate schedule, as our current experiments treated it as negligible. A mismatch between our model's form and the actual dependencies could clarify the inconsistencies we see at the beginning of training, which does not fit as well as later stages. Our work builds on numerous recent studies that link scaling law estimation to model training decisions. These studies examine various factors, including training costs, data selection, training time, and model behavior across different modalities. Particularly relevant to our work are studies that utilize multiple pre-training settings to create scaling laws that apply broadly across models. We acknowledge some limitations in our study. Our primary evaluation metric, R, does not differentiate between over- and underestimation of performance. This could lead to overly cautious error estimates when selecting between candidate models. Another significant limitation is the challenge of aggregating information across different model families, as many published models operate on incomparable scales and ranges. This made it difficult for us to create a comprehensive figure that could provide general recommendations for optimal preliminary experiments.